Hello students, welcome back. We just completed section 3 of this notebook, the matrix exponential, which was essentially a review from the previous week. Now let's go to section 4, the Laplace transform of the matrix exponential. What is this all about? Let's begin with a motivating example, this one. Let's minimize this one and let's focus on the first problem here. Let's consider a first-order system of homogeneous linear ODEs like this. And let us simplify this expression using the matrix expression like this. Please note that if you take these substitution, capital Y of t as the column vector function, x of t, y of t, and capital A as this matrix in the middle, and capital Y star as the initial condition, then this whole thing here, this whole system, can be written like this. The bold part is the ODE part, and this one we are just highlighted in green is the initial condition. This one let us highlight in blue. What did I click? Okay, alright. Blue is the ODE part, green is the initial condition. Okay, here I claim this is the formula. If we accept this formula as the solution, that's the assumption number 1. And assumption number 2, if we accept this is the matrix exponential computation, under these two assumptions, the computation becomes really simple. Assumption number 1, this formula, which we are about to check right now, and assumption number 2, this matrix exponential, which we'll talk about a little later. First, the formula. How does it work? If this is true, and take the derivative, then y prime is equal to, let's see, this is constant coefficient, just multiplied by constant, so it doesn't change. This is exponential, so exponential never changes, so they both stay the same. But then again, by chain rule, we have to multiply the derivative of the inside. Now, what is the derivative of A times t? Hint, A is a constant matrix, constant coefficient. So what's the derivative of A times t? It's just A. So by chain rule, we multiply by the derivative of the inside, which is A, and here is the derivative computation. Now, what is this exponential times y star? That's y of t. So this whole thing is equal to A times y. And what do we have? We got the desired ODE. We got the blue part. So if this is the case, then we are halfway through. We got the ODE. How about the initial condition? Okay, here plug in t equal to 0. Then we have e to the a times 0, but then again this is scalar multiplication. Multiply 0 to each entry here, then everything will become 0 and you're going to get a 0 matrix. Times y star, and what is e to the 0? E to the 0 power is identity matrix, so this is y star. So we got the initial condition as well. So the green part corresponds to the IC, and the blue part is the ODE part. Make sense? So this is valid. This formula here is valid formula. Okay, I admit there's a bit of a hole here. Nothing's wrong here. Just plugging in t equals to 0, and we have e to the 0 power is identity, so everything works out. Nothing's wrong here. Here, there's a bit of a hole. In this derivative computation, how does the chain rule apply? There's something to fill in, but that's something we are going to fill in later. For the time being, let's accept this. This formula works out just fine. Is it usable? Oh yes, it is. If we can calculate the matrix exponential, the red part. If we have it, then it works out. So the key turns out to be the matrix exponential computation. In this particular case, for this particular example, it goes like this. This is a matrix A, and then this is the Taylor series expansion of exponential, and this is coming directly from the definition. And then from here, we want a to the k power times t to the k power. So let's calculate those, and here are some brute force computations, my goodness. All these. And then in the end, we find some pattern. We were lucky to find out pattern. Using the pattern, plug everything back into the Taylor series expansion here. Then we get the Taylor series expansion for each entry. And then we look for pattern for each entry, and luckily, times 4, we got appropriate pattern for all 4 entries, and then we ended up with this matrix, which we have right here. So what's the conclusion? How tedious and complicated was it? But then again, that pales to the next consideration. How lucky were we? We were extremely lucky 5 times. And a method that relies upon that kind of luck is simply not good. We need a better tool. It may have worked out here okay, and it'll work out pretty much the same way for this one, which I leave for homework problem. But in general, it's not good because we rely too much upon luck. We need better tool, and the tool that we are going to be focusing upon in this section is the Laplace transform method. Basically, this is where we are up to. We want this formula here, which I just highlighted in bold. This is something we want to establish. If we want the matrix exponential, then according to this formula here, all we need to do is to find out this inverse matrix, which we call the resolvent matrix. Name is not that important. In any case, this is just the inverse matrix computation. And then take the Laplace inversion. So, if you have a 2 by 2 matrix, then inverse is not too bad. We have inverse matrix formula. And then take the Laplace inversion. We have 4 components. So taking the Laplace inversion of all 4 of them, okay, it takes some effort. We need some decomposition by partial fraction, but you can handle it. That's about I expect for this course. And all the essential things are in 2 by 2 form, nothing bigger. And for 3 by 3 or higher, I'm going to consider some of those in lesson 15, but all those are going to be optional. As for 2 by 2, yes, we can handle it. Inverse, you can handle it. Laplace inversion, okay, just 4 times, you can handle it. Do you want to see an example? Okay, here's an example. Of course, I'm not going to complete it. Excuse me, I need this formula back. Okay, this is a formula we want. And then for this matrix, step 1 is to find out this inverse matrix right here, which we call the resolvent matrix. So Si minus A, so that's going to be a polynomial expression of this 2 by 2 matrix. And then taking the inverse of 2 by 2, that's not too bad. And then take the Laplace inversion of each entry. So we have 4 Laplace inversions to take. Then you're going to get the matrix exponential. This is a concrete method that we are going to be using. Oh, one more thing here. I almost forgot. No, excuse me, no. right here. Please make this recognition. If we go back to one-dimensional function, the usual real function, this is a Laplace transform formula for the usual one-dimensional real exponential function. And this is a Laplace inversion. Change it to small a. So, do you see a correspondence here? We have a division, 1 divided by s minus a, and here we cannot divide by matrices because there are plenty of non-invertible matrices. So we have to take inverse matrix if the inverse exists. So there's a bit of a ramification here, but still this corresponds precisely to this one. And same goes here. This corresponds precisely to that one. So there is a connection between one and the other. By the way, about this, if you forgot and if you have to look those back up, please go back to page 123, the Laplace table, and look those up again. And we have been going back to the same table in the page 123 so many times, probably by dozens of times by now already. So I hope everybody memorized those already. But if you didn't, there you go. Anyway, that's where we are headed. And then once you have this matrix exponential, then matrix exponential times either initial condition or in general C1, C2, then you're going to get the solution of your system. I mean C1, C2, what am I talking about? I'm talking about this. If this is C1, C2, and if this is C1, C2, and voila, I have the general solution. This is the unique solution of this initial value problem, and this one is a general solution when the initial condition is not present. Either way, the key point is the matrix exponential, because we already established this. Okay, there are a little bit of holes to fill in, but we established it. So the key point is the matrix exponential, and that's something we are going to focus upon. Okay. So much for the motivation and the overview. Let's stop here, and then we're going to come back and discuss the rest of the section in the separate videos.